Download this code from codegive.com, link in the description below. OK, let's delve into the world of chemical industrial accidents, their causes, prevention, and some rudimentary Python-based modeling for risk assessment. This is a complex topic, so we'll break it down into manageable sections. Introduction: the significance of chemical industrial accident awareness. Chemical industrial accidents are a serious concern. They can lead to loss of life and injuries, the most immediate and tragic consequence. Environmental damage, release of hazardous materials contaminates air, water, and soil. Economic disruption, facility damage, production losses, and cleanup costs. Reputational damage, erosion of public trust and potential legal liabilities for companies involved. Long-term health effects, exposure to certain chemicals can result in chronic illnesses. Learning about the causes, consequences, and prevention strategies for chemical accidents is crucial for engineers and plant operators to design and operate safer systems. Safety professionals to develop and implement robust safety protocols. Regulators to create effective regulations and enforcement mechanisms. The general public to understand potential risks and advocate for responsible chemical management. Emergency responders to be prepared for incidents and mitigate their impact. 2. Types of chemical industrial accidents. It's essential to understand the different types of accidents that can occur. Here are some common categories. Fires and explosions. BLEV, boiling liquid expanding vapor explosion, a catastrophic explosion occurring when a vessel containing a pressurized liquid fails, often due to external fire. Vapor cloud explosion, VCE, the ignition of a large cloud of flammable vapor in the air. Dust explosions. Combustible dust particles, example coal dust, grain dust, metal dust, dispersed in the air and ignited. Releases of toxic chemicals. Gas leaks. Releases of toxic gases, example chlorine, ammonia, sulfur dioxide. Liquid spills. Spillage of hazardous liquids, example acids, solvents, into the environment. Runaway reactions. Uncontrolled chemical reactions that generate excessive heat and pressure. Equipment failures. Pressure vessel ruptures. Failure of pressure vessels due to corrosion, overpressure, or material defects. Pipeline leaks. Leaks from pipelines transporting hazardous materials. Storage tank failures. Failures of storage tanks due to structural weakness or overfilling. Transportation accidents. Tanker truck accidents. Accidents involving trucks carrying chemicals. Rail car derailments. Derailments of trains transporting hazardous materials. Ship collisions. Collisions involving ships carrying chemicals. 3. Common causes of chemical industrial accidents. Identifying the root causes of accidents is vital for prevention. Some major contributing factors include 1. Human error. Operator error. Mistakes made by plant operators, example improper valve settings, incorrect procedures. Design errors. Flaws in the design of equipment or processes. Maintenance errors. Inadequate maintenance leading to equipment failures. Management failures. Lack of adequate safety training, supervision, or safety culture. 2. Equipment failure. Corrosion. Deterioration of materials due to chemical attack. Wear and tear. Gradual degradation of equipment over time. Asterisk material defects. Asterisk flaws in the materials used to construct equipment. Asterisk overpressure. Asterisk exceeding the design pressure of a vessel or pipeline. 3 process deviations. Asterisk runaway reactions. Asterisk uncontrolled chemical reactions that generate excessive heat and pressure. Asterisk unexpected chemical reactions. Asterisk unforeseen reactions between chemicals. Asterisk contamination. Asterisk introduction of unwanted substances into a process. 4 external events. Asterisk natural disasters. Asterisk earthquakes, floods, hurricanes, and wildfires. Asterisk sabotage. Asterisk intentional damage to equipment or processes. Asterisk cyber attacks. Asterisk attacks on computer systems that control industrial processes. 5 inadequate safety management systems. Asterisk lack of hazard identification and risk assessment. Asterisk failure to identify potential hazards and assess their risks. Asterisk poor emergency response planning. Asterisk inadequate plans for responding to accidents. Asterisk insufficient training. Asterisk lack of adequate training for employees on safety procedures. Asterisk weak safety culture. Asterisk a culture where safety is not prioritized. 6 communication failures. Asterisk unclear instructions or procedures. Asterisk lack of communication between different departments. Asterisk inadequate communication during shift changes. Asterisk failure to communicate hazards or warnings effectively. 7 regulatory non-compliance. Asterisk violations of safety regulations and standards. Asterisk failure to obtain necessary permits and licenses. Asterisk inadequate enforcement of regulations by government agencies. 4. Prevention strategies. A multifaceted approach is necessary to prevent chemical industrial accidents. 1. Inherently safer design, ISD. Asterisk minimization. Asterisk use smaller quantities of hazardous materials. Asterisk substitution. Asterisk replace hazardous materials with less hazardous ones. Asterisk moderation. Asterisk use less hazardous process conditions, example lower temperatures and pressures. Asterisk simplification. Asterisk design processes that are easier to understand and operate. 2. Hazard identification and risk assessment, HIRA. Asterisk hazard and operability studies, HAZOP, a systematic method for identifying potential hazards and operating problems. Asterisk failure modes and effects analysis, FMEA, a method for identifying potential equipment failures and their effects. Asterisk fault tree analysis, FTA, a deductive method for identifying the causes of an accident. Asterisk event tree analysis, EDA, an inductive method for analyzing the possible consequences of an initiating event. Asterisk quantitative risk assessment, QRA, a method for quantifying the risks associated with a hazardous activity. 3. Process safety management, PSM. Asterisk written operating procedures. Asterisk detailed instructions for operating equipment and processes. Asterisk training. Asterisk adequate training for employees on safety procedures. Asterisk pre-startup safety reviews, PSSR, reviews to ensure that new or modified equipment and processes are safe to operate. Asterisk mechanical integrity. Asterisk ensuring that equipment is properly maintained and inspected. Asterisk hot work permits. Asterisk permits required for activities that may create a source of ignition. Asterisk management of change, mock procedures for managing changes to equipment, processes, or procedures. Asterisk incident investigation. Asterisk thorough investigation of accidents to identify root causes and prevent recurrence. Asterisk emergency response planning. Asterisk plans for responding to accidents. Asterisk audits. Asterisk regular audits to assess the effectiveness of PSM programs. 4. Safety culture. Asterisk Asterisk leadership commitment. Asterisk strong commitment to safety from management. Asterisk employee involvement. Asterisk employee participation in safety programs. Asterisk open communication. Asterisk open communication about safety concerns. Asterisk continuous improvement. Asterisk a commitment to continuous improvement in safety performance. Asterisk accountability. Asterisk holding employees accountable for safety performance. Asterisk recognition. Asterisk recognizing and rewarding employees for safe behavior. 5. Emergency response planning. Asterisk emergency shutdown procedures. Asterisk procedures for safely shutting down a process in an emergency. Asterisk evacuation plans. Asterisk plans for evacuating personnel from the area. Asterisk first aid and medical care. Asterisk providing first aid and medical care to injured personnel. Asterisk firefighting. Asterisk extinguishing fires and preventing explosions. Asterisk hazardous material spill control. Asterisk containing and cleaning up hazardous material spills. Asterisk communication with the public. Asterisk communicating with the public about the accident and its potential impact. 6. Regulation and enforcement. Asterisk robust regulatory frameworks that define safety standards and requirements. Asterisk effective enforcement of regulations by government agencies. Asterisk regular inspections and audits of chemical facilities. Asterisk penalties for non-compliance with regulations. V-Code example, simple risk assessment using Python. This example demonstrates a very basic risk assessment framework using Python. Keep in mind that real-world risk assessments are far more complex and require specialized software and data. This code is for illustrative purposes only. Explanation of the code. Asterisk chemical risk assessment class. Asterisk this class represents a risk assessment for a specific chemical-related scenario. It encapsulates the hazard, likelihood, and provides methods to calculate the risk score and level, and recommend mitigation measures. Asterisk underscore init underscore method. Asterisk the constructor initializes the chemical risk assessment object with the hazard and likelihood scores. Asterisk calculate underscore risk underscore score method. Asterisk calculates the risk score by multiplying the hazard and likelihood scores. This is a very simplified approach. More sophisticated risk assessments might use a risk matrix or other more complex formulas. Asterisk determine underscore risk underscore level method. Asterisk determines the risk level, low, medium, high, based on the calculated risk score. The thresholds used here are arbitrary and should be adjusted based on the specific context of the assessment. Asterisk recommend underscore mitigation method. Asterisk provides generic mitigation recommendations based on the risk level. Asterisk estimate underscore hazard underscore score and estimate underscore likelihood underscore score functions. Asterisk these functions are extremely simplified examples to show how you could potentially incorporate more data into the risk assessment. They take into account factors like chemical toxicity, quantity involved, historical frequency of incidents, and the reliability of safety systems. Important notes on the code. Asterisk 1. Simplification. Asterisk this is a highly simplified example. Real-world risk assessments are much more complex and require more detailed data, specialized software, and expert judgment. Don't rely on this code for actual risk assessment in a chemical plant. 2. Data quality. Asterisk the accuracy of the risk assessment depends heavily on the quality of the input data. You need accurate and reliable data on chemical properties, equipment failure rates, human error rates, and other relevant factors. 3. Context. Asterisk the appropriate risk assessment methods and thresholds will vary depending on the specific context of the assessment. Consider the type of chemical, the scale of the operation, the location of the plant, and other relevant factors. For risk matrices *, a common technique is to use a risk matrix, where hazard and likelihood are categorized, e.g. low, medium, high, and the matrix cells define the overall risk level. The thresholds for these categories need to be carefully chosen. 6. Further development and considerations. To make this code more useful, although still for educational purposes, not professional deployment, you could consider the following. Database integration *, store chemical properties and safety data in a database, example SQLite, PostgreSQL, and retrieve it using Python. GUI development * create a graphical user interface, GUI, using libraries like tkinter or pyqt to make the risk assessment tool more user-friendly. Integration with simulation software * link the risk assessment tool to process simulation software, example Aspen HYSYS, to simulate potential accidents and assess their consequences. Uncertainty analysis * incorporate uncertainty analysis techniques, example Monte Carlo simulation, to account for the uncertainties in the input data. Sensitivity analysis * perform sensitivity analysis to identify the factors that have the greatest impact on the risk assessment results. Consequence modeling * use specialized consequence modeling software to simulate the impact of chemical releases, fires, and explosions. Layers of protection analysis, LOPA, a semi-quantitative technique used to assess the adequacy of safeguards in place to prevent or mitigate an accident. 7. Regulations and standards. Many regulations and standards govern the safety of chemical industrial facilities. Some key ones include OSHA's Process Safety Management, PSM, Standard, 29 CFR 1910.119. The standard covers the management of hazards associated with processes using highly hazardous chemicals. EPA's Risk Management Program, RMP, Rule, 40 CFR Part 68. This rule requires facilities that use extremely hazardous substances to develop and implement risk management programs. National Fire Protection Association, NFPA, standards *. NFPA standards cover a wide range of fire protection and safety topics, including the storage and handling of hazardous materials. International Organization for Standardization, ISO, standards *. ISO standards provide guidance on quality management, environmental management, and occupational health and safety. 8. Ethical considerations. It's crucial to address the ethical implications of chemical industrial activities. Transparency * be open and honest with the public about the risks associated with chemical facilities. Community involvement * involve the community in the planning and decision-making processes for chemical facilities. Environmental justice * ensure that chemical facilities are not disproportionately located in communities that are already overburdened by pollution. Accountability * hold companies accountable for accidents and their consequences. Worker safety * prioritize the safety of workers in chemical facilities. 9. Conclusion. Chemical industrial accidents pose significant risks to human health, the environment, and the economy. By understanding the causes of accidents, implementing effective prevention strategies, and promoting a strong safety culture, we can significantly reduce the likelihood and severity of these events. The code example, though basic, illustrates how computational tools can play a role in risk assessment, but should always be used with expertise and understanding of the underlying principles and limitations. Remember that safety is an ongoing process that requires continuous improvement and vigilance.